Okay, so the key statistics that we've calculated in previous videos can tell us a lot about the shape of our data. But in order to really understand the patterns that dictate our mean and the other figures we've calculated at a more kind of intuitive level, we need to get a better sense of how governments are distributed along our range, stretching from under $1 to well over $6,000 in some of our years. Are, for instance, nearly all of our governments spending less than our mean in any given year? Perhaps the mean averages we've calculated are being pushed up by a few exceptional outliers who spend many thousands per head per year. Now, you could tell some of that from the key statistics and comparing them, especially if you were using the interquartile range and the percentiles. But there's a much more intuitive way, which is to create what's called a frequency distribution table, and then in the next video we're going to chart that into a histogram. So the way we're going to get that overall picture of government health spending is to construct a frequency table. Now, I'll say a little bit more about these in class next week, but basically a frequency table tallies up how many values fall into a set of bandings. In our case, how many countries fall into spending bandings like less than $100 or more than $2,000. We're going to construct frequency tables for both our overall 95 to 2010 data and then for each of our sub-periods. Now, thankfully, Excel does the hard work for you here, so you're not going to need a pencil and paper tallying up how many governments fall into each spending band or anything like that. There's a really nifty way that Excel can do that for you, and you can apply this technique in your projects, whether they're about kind of, I don't know, a sample of if it's human biological data or about heights is the classic example for this, or whether it's to do with number of cultural heritage sites in Spain, Portugal, features of a language, whatever. Anything where you're looking at how your data is distributed between the different variables, between the different data points you have, so with nations, people, councils, whatever, then this will be useful, this technique, for you. So first we need to decide upon some bandings that we're going to split our data up into. Now in data science or statistics we'd call these bins, and if you've done A-level statistics you'll be very familiar with these probably. So imagine that we had a simple data set, and I'm just going to do it here and I'll delete this for you, that had completely random numbers that ranged from 1 to 30. There's only going to be 10 numbers, but the maximum they could be is up to 30, and so I'm just going to randomly put some in now. Okay, so there they are. We have a list of random numbers, 10 random numbers that can range from potentially from 0 to 30. But we've got what we've got. Okay then, so if we set a first bin at 10 or less than 10, so equal to or less than 10, then all the numbers that are in this list that are 10 or less than 10 are going to fall into that first bin. So the 5s are here, so we're going to have these 3 and the 10 itself. And then plus all these 5s down here. So we've got 5 5s there, 6, 7, 8. So we're going to have 8 of our numbers have already gone. They've already fallen into that first bin, which is less than or equal to 10. Now, if we had a second bin set at less than or equal to 20, then all the numbers in the range of 11, so too big to fit in our first bin, up to 20 are going to fall into that. So we're talking really just about this 15 here. So we're going to have one of our numbers falls into that. And then all of those between 21 and 30 are going to fall into our final bin in this very fake data set, which would be equal to or less than or equal to 30. And the only one that we've got that fits that description is this 29 here. So the resulting figure that we've associated with each of our bins isn't a kind of sum of these. It's not 5 plus 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 10. It's just literally 8, because that's how many of our values fell into that bin. So apologies if I'm teaching stuff that you well already know from GCSE statistics onwards, but I think it's best that we're clear about what these bandings actually are and what the numbers you're putting next to them are going to represent. So basically the resulting figure associated with each of our bins would be how many of the numbers from how many of our the items in our data set, in this case numbers, random numbers, fall into each of those bins. Okay, let's just get rid of that for now. But there is a question, especially with more complicated data sets, about which points we should set our bins and the cutoffs for them, if you like. Now, there is no surefire way of knowing this. It's a matter of judgment. But knowing the key statistics above, like the max, the min values, the mean, the median, etc. of our data, is helpful because we can at least construct bins that we know are going to cover most of our countries or most of the data points in our series. In our set. So ideally our bins would also be of equal width, i.e. they're going to cover the same range of values. But some outliers in our data set, so isolated values at the extremes of our range, are going to make that difficult, and we'll see why in a moment. So in our 2007 to 10 data, for example, we need our frequency table to be able to cope with range of values from $1.64 through to $6,000 and $6,876. Now this means that if we were to say start at the first bin ending at $5, so equal to $5 or less, and the next one at 10, we increased that by 5, so the next one was $10 equal to or less, then we'd end up having to have a frequency table that extended to well over 1,000 rows to cover that full range of data from $1.64 through to nearly $7,000. Now, one solution is to have our bins cover more ground. So perhaps we could start with a bin set at $100 and then move up in hundreds at a time. So anything less than or equal to $100 would go in the first bin, and then we'd have $101 to $200 in the second bin. So we'd be moving up in a larger bin width, if you like, through larger bandings. Yet this is still going to result in over 60 rows, and it's going to have also lumped all of those lower values together, meaning that we're going to lose any sense of how many countries might have moved up from $1 to $100 per capita spending per year in our time periods, because they'd always be falling into that very wide first category. So we're going to lose some definition, if you like, as to the actual distribution of our data at the lower ranges when we make the bins wider in order to have fewer of them. So there's a trade-off going on here. Now, the only real solution is to accept that we'll have to choose bands that attempt to cover most of our data, but that these are going to distort things at the extremes, either low values or very high values. We're going to have less definition of how things are actually distributed. I've decided to set my bins for the following example I'm going to show you at $50 increments. So therefore my first bin is going to cover values between 0 and 50, or actually technically the way we're doing it could theoretically include minus figures because it's less than or equal to 50. The second bin is going to then cover values from 51 to 100, so effects, we're going to say the bin is less than or equal to 100 and so on, and then we'd increase by another 50, so we'd have one less than or equal to 150. So when I'm quoting that figure, it's always the top edge of the banding, if you like, that you're giving as the cutoff point for what's in the bin or not. So we're going to have to accept when we've done that to show the data at the lower end of the scale, where most of it unfortunately is, or the interesting stuff is, then the much smaller number of countries, we're going to have to focus on that lower end, rather than the much smaller number of countries who are spending over $1,000 or greater, because I can't continue on adding those $50 increments, otherwise I end up with an absolutely huge table. So the solution is going to be that when I get to 1,000, or 1,001 or greater, basically, greater than 1,000 will be the bin, not greater than or equal to, but greater than $1,000. We're going to have this as a final bin that puts all of those really high spending countries together and tallies up how many of them there are. Now again, we're losing definition there because it lumps together people spending $1,001 with those who are spending $6,000. So it's a simplification, but I think it's the best one available to us, because although we could do some fancy stats to make if we charted this to kind of have different bin widths and make the areas different to reflect that on the chart, I think the most honest way to do this for your readers, to be honest about the kind of distortions and lumping together things that you've done, is sometimes to have a final category on your graph that says anything over this amount is going to be put in there, and then make sure you tell them what the min and max values are so they can make a judgment about why that's being distorted, why there are likely to be, to look like there are a lot of values in that, but they're actually spread out between, in our case, $1,001 and $6,000. So I hope you're getting a bit of intuition to this. I think it'll make more sense when we get down to making the frequency table now. So in cell X17, which is 2 rows below our statistics table, so over here, I'd like you just to type the title, bins less than or equal to. This is where we're going to put our list of bins that we'd like Excel to use. And then we're going to start by doing this for our overall data. So for the sake of it, let's unhide 95 to 2010 column so we can make everything line up. And then in Y17, let's just type the range we're working with, the time frame we're working with, 95 to 2010, the overall stuff. And then you can format it if you want to look a bit more like a table. So let's start typing the bins then. Remember that the number that we give here in our list of bins, we're giving the upper edge. So it's always equal to and less than is what these numbers represent. So the first one we said was going to be 50. So this should be in cell X18. So this is telling Excel the first bin represents, it's going to contain all the how many nations are there that fall into the $50 or less spending category. And then the next one, we are going to do next 19, we're going to put in 100, so less than or equal to 100, and it knows that it's not to include values that are that fall into both of these. So basically here you're only going to get values from 51 to 100 in reality. So it's not cumulative in that sense. And then we said we wanted $50 increments going up to 1,000. So the quick way you remember in Excel of doing that is to highlight both of these. It's going to calculate the difference between the two, and as we drag down, it increments up. So let's go down to about there and a bit further for 1,000. There we are. Now for the tallying, and it's really crucial that you follow really carefully. Both I'd get the written instructions out as well as following along on the screen, because the exact kind of key presses and the way you type things in here really matters. It's quite easy to mess this bit up in Excel. So what we need then is for Excel to know where the data it needs to start tallying is coming from, and it needs to know something about these bins, as well as, I guess, knowing that what we want it to do is calculate, is to go through our data. So for 95 to 2010, that one here, the means, the overall average means, and we want it to calculate how many of these fit into each of our bandings. And the way we do that is select not this time just a cell, but a range from, I think, X18 down to X38, or is it? Just check. Yeah, that's extra. So it's one extra than you might expect, basically. So, sorry, it's Y18. I'm wrong. Y18 down to Y38. Now, without pressing anything or losing this selection, I just want you to hit F2. And this just takes us into entering a formula mode, or entering values. It's a quick way rather than just double clicking or anything. And it's safer to do this because it prevents you from losing the selection, basically. So pressing F2 to get the cursor up, and we're going to start typing a formula. And that formula is equals frequency, open your brackets, give it the range of where our data is. It's not R2 anymore because we added an extra row when we did our inflation adjustment. So it's R3 down to R267. And we can check that it's got the right range in a moment, but R267, and then comma, because we've given it where it's going to, the data it's going to tally for us. We now just need to tell it where the bins it's to split that data up by are lying, and they lie at the moment in cells X18 to X37. There we are. And close the brackets. Make sure you put a comma in to start, make sure between when we gave it the first range and the bins range. And then don't press enter yet. What I need you to do is press Control, Shift, and then enter. So you're holding Control and Shift and then pressing enter, and you should get what's called an array formula. We can tell it's turned it into an array formula because it's put curly brackets around the formula. And what this tells Excel to do is, instead of just generating one single value in one cell, it's to carry out the process of that frequency counting, tallying, and result in a list of values. in the cell range that we highlighted, and that's why it was really important that we highlighted that full. When we started this, we highlighted a space for the list to go, rather than just clicking on one cell and typing the frequency formula. So key thing then, if you're on a Mac, is obviously to press Command, Shift and Enter rather than Control. But the key thing is to be holding down Control and Shift when you then eventually press Enter to finalize the formula. So this is a bit tricky on Excel, so make sure that you're getting the same result I am with tallying up, not one with errors in, or what more looks like a kind of cumulative table where it's just adding every previous result. Typically that's happened if you've not managed to select the data right or press the keys in those order. So we selected, when we carried out the selection of where this formula was going to go, we selected one more row down here than you might have assumed we would. And the reason we do this is Excel really likes to have an extra space in which it can put anything that doesn't fit within these bins. And that's really convenient for us because the only things that don't fit within our bins range here are values that are over 1,000. So they're over $1,001 and up, basically. And that, of course, is what I was saying that we wanted to have in this table. We wanted a category or a band or a bin that was deliberately bigger, that was just going to cover everything above $1,000. And so what we can conveniently do then, and you need to do this regardless, Excel, that formula really needs to have somewhere to put how many values don't fit into your bin. So you always would put an extra one at the end and not make it in your bins, not define that bin. You'd leave it until afterwards. So basically Excel needs to have somewhere that it's putting the formula into a selection of rows that is one longer than the number of bins that you've got, so it has a spare place to put anything that doesn't fit. And we can go back in afterwards though and go and remind ourselves that this represents values that are greater than $1,000, not equal to $1,000, just greater than. So long and short is you always need a spillover bin that's not initially defined, so that Excel can calculate how many things don't fit or are greater than your the final bin you've got, and you can go in afterwards and relabel this. Okay, in the next video we're going to show you how to chart this in the traditional way using a histogram.